Okay, so we have a spring here at its unextended length, at its natural length. We put a pendulum on it, on a ball or whatever, so it's stretched, right? So this is the equilibrium position. You displace it, maybe you pull it down here, and then you let go, and it's going to oscillate between the top and the bottom positions. So how would the various forms of energy change as it goes from bottom to equilibrium to top to equilibrium to bottom as it oscillates, as it oscillates. So I think the first one I would like to sketch would be the kinetic energy, Ke. Kinetic energy is of course half mv squared, and you know that the oscillation is at rest at the extreme positions. So Ke is 0 at the extreme positions, and it's maximum when it's at the equilibrium position. And it's going to be a quadratic curve. Is it quadratic? Yeah, quadratic curve. So this will be Ke is given by half mv squared. It has got to be a quadratic curve. Maximum at the equilibrium, 0 at the extreme positions. The next one, maybe I would sketch the GPE. So the GP at the bottom has got to be the lowest, and at the top it has got to be the highest. So from the lowest to the highest, that will be GPE. It's a straight line graph because GPE varies linearly with the vertical height. So our x-axis is, you can basically see it as a height, right? So as the height increases, the GP also increases in a linear fashion. Alright, that's why it's a straight line graph. Now, you know, for GP we can set our reference to be anywhere we want. So even though we know it's a straight line graph, it could easily have been this, or this, or this. It all depends on where you set your GPE to be 0 at. Alright, so it's a straight line graph that can be shifted up and down to our liking. Okay, the next one I want to sketch is the elastic potential energy graph, EPE. So notice that even at the top position, when it's least stretched, elastic potential energy is not 0, alright? Elastic potential energy is 0 when the spring is unstretched, but at the top position it's already stretched, so we should have some amount of elastic PE even at the top position. And as we go towards the bottom position, the spring becomes more and more stretched, so the EPE graph will increase as we go towards the left. But it will not increase in a linear fashion. Instead, it will be a quadratic graph. Alright? That's because elastic PE is given by the formula half kx squared, where x is the extension. So you can see this, our x-axis going leftward as a increase in extension. So as the spring becomes more and more extended, the elastic PE increases, but it increases in a quadratic fashion. That's why it must be a curve. Alright? And the last one, the obvious one, is if you add up these three forms of energy at every position, they should add up to be a constant. So total energy is going to be a horizontal line. Okay? So just to recap, GPE must be a straight line graph, KE must be a quadratic curve, an inverted U shape, elastic PE must not be a straight line, alright, because it's a quadratic curve.